Hey everyone, my name is Kanahaiya Gupta and welcome to my YouTube channel. Today we are going to discuss knapsack problem and its solution using dynamic programming in detailed manner. So before moving ahead, make sure you are subscribed to my YouTube channel and click the bell icon so that you don't miss any update. Let's start. So in today's lecture, I am going to cover knapsack problem and its variants, and that we will cover 0-1 knapsack problem and the fractional knapsack problem. Then we will see the standard problem statement for 0-1 knapsack problem. Then we will see the example. After that, we will take one subproblem and try to solve it, and we will use the table filling approach to solve that problem. Then we will see the step-by-step thought process to derive the algorithm for solving the problem. Then we will use FAST method to solve this DP problem. In that, we will first calculate the recurrence relation and we will try to derive the recursive solution out of it. Then we will analyze the solution and the complexity. Later, we will use the top-down approach or memoization technique, and we will see the two variants, caching on global level and cache passed as a method argument. And finally, we will convert this solution into a bottom-up manner, which is also called as tabulation. Then we will do some pattern analysis, and at the end, we will see the demo. So guys, this is all we are going to cover in this lecture. Guys, this tutorial is going to be a little bit lengthy, but trust me, if you watch this tutorial till the end, you will not have any doubt in the knapsack problem. Let's start. So this is the standard problem statement, guys. Given a set of n items, each with its own value vi and weight wi for all where I ranges from 1 to n, and a maximum knapsack capacity c, compute the maximum value of the item that you can carry. This statement may look puzzling right now, and we'll go more deep into it, but before that, we'll understand what are the variants of this problem. Knapsack problem variants. Knapsack problem has two variants. One is 0-1 knapsack problem, and second is fractional knapsack. The problem which follows these properties comes under 0-1 knapsack problem, where items are indivisible. You cannot take the fraction of any item. So you have to take only the binary decision. Either you have to take it or leave it. That is why it is a 0-1, which requires dynamic programming approach to solve this problem. In the fractional knapsack, items are divisible, where you can carry the fraction of the item along with you, and which requires greedy approach to solve this problem. As we are working on a dynamic programming examples, so we are going to deal with 0-1 knapsack problem, and our problem statement follows these properties, which we will solve using dynamic programming. So now I hope it is clear what we are going to discuss in this complete lecture. So this was the standard problem statement. Let me add few pointers here. Now this example is a proper problem statement for 0-1 knapsack problem. So here you can see the highlighted part. So you cannot take fraction of item along with you, which clearly says it's a 0-1 knapsack problem. So this is the problem statement, and this is the input for this problem statement. Suppose we have an input where values are 10, 40, 30, 50, and weight of the items are 5, 4, 6, 3, and our knapsack having a capacity is 10. So what is the maximum value which we can carry along with us in a knapsack? So the complete information of the input can be represented in terms of table like this, and the output for this problem statement will be 90. If you choose value 40 and 50, you will get the result 90. Why we are going to choose 40 and 50? Because this is the max which we can obtain from this information. 40 with weight 4 and 50 with weight 3. So the total weight we can carry is 7, and total value which we will be getting as a profit is 90. As our knapsack is having a capacity of 10, so we only carry maximum weight less than equals to 10, and 7 is less than 10. So the answer for this problem is 90. So this is a standard problem statement, guys, and the input and output, but it's very difficult to understand what is the logic behind it. So what we do, we always try to solve the problem step by step. If you are not able to get it, just try to solve this problem for small amount of input and see the output. So for that, I have just derived a problem from this generic problem, which is called a subproblem. So here is a subproblem. Suppose you are a thief, you are in a store with a knapsack, and there are all these items you can steal. But you can only take what you can fit into your knapsack. The knapsack can hold 4 lbs as a capacity, and you are trying to maximize the value of the item you put in your knapsack. So this is the input, guys. Here you will get the values of 150, 300, 200, and these are the item weights 1, 4, 3, and this is the capacity of the knapsack, which can be represented in terms of table, something like this. Here unit can be anything, guys. Here for value we have taken dollars, and for weight we have taken lbs, but it can be anything. So for now, do not consider unit. You have to do the calculation based on the numbers, whatever is given to you. Now the problem statement is very clear, guys, and we have to come up with a solution so that we can carry maximum value in our knapsack. To solve this problem, let's take a table where rows represents item, phone, laptop, tablet, and column represent weight 1, 2, 3, 4. So why we have taken a table, guys, here? Because our solution depends on two things: which item we are choosing, and based on that weight is also varies. So we have to consider these two properties to come up with a solution. So on the left side you can see all rows shows the items and the column shows the capacities. Here we have given a capacity of 4. If capacity is 4, so we can always carry the weight less than equals to 4. So that is the reason I have taken a column as a 1, 2, 3, 4. It means the weight we can carry with the 1 lbs, 2 lbs, 3 lbs and 4 lbs. Now we'll try to solve this problem step by step. For now, just focus on row 1. So just think about like you have only one item to steal with. So if you have only one item and capacity of your bag is 1 lb, then what is the max profit you can get? It's 150, right? Because you can carry the mobile with you. In the similar way, if you have knapsack of capacity 2 and you have only one item to carry, how much profit you can make? 150, right? In the similar way, if you have a knapsack with capacity 3 and you have only one item mobile to steal with, how much profit you can make? 150. In the same way, if you have a knapsack of capacity 4 and you have only one item to steal with, the max profit you can make is 150, right? Let's try to make this problem a little bit complicated by introducing one more item. So now you have two items with you. Now you have to make a decision to get the maximum profit, what you will choose. For the second row, now you have two options. Either you can choose the laptop and the item above it. So we have phone and laptop for the second row. So let's fill this table. If your knapsack is having a capacity of 1, then what you can choose right now? You can't choose the laptop for the laptop. So what is the maximum profit you can make is depend on last row which you have filled it. So what is the maximum profit you achieved so far? It will be 150, right? We have just copied from the above row. In the similar way, for the second column, if the knapsack is having a capacity of 2, can you choose the laptop? No. So what is the maximum profit you will get? The maximum profit achieved in the last time or the last row, or maybe you can say from the above row. So what is the maximum profit you will achieve? 150. So you will copy the profit from the above row. In the similar way, for the third column, the knapsack is having a capacity of 3. So can you choose the laptop right now? No, because laptop is having a 4 lbs. So what is the maximum profit you can make it here? Is a 150. We will copy from the above row. And for the fourth column, now the capacity is 4. So can you choose the laptop right now? Yes. What is the maximum profit you are achieving from the upper row or what is the maximum profit you have achieved so far in the past? 150. But now you have option of taking a laptop worth rupees $300. So what you will choose? Definitely you will choose the laptop of worth rupees $300. So this is the maximum profit which we can make with knapsack of capacity of 4 lbs. Let's try to fill the next row. So next row we have tablet. So let's introduce some more complexity in this. Now we have a third item with us, which is a tablet. So for the last row we can choose the item tablet or the item above it. So we have laptop and phone also. So if you have knapsack of capacity 1, so what is the maximum profit you can make? You can't pick the tablet here because tablet is having a 3 lbs. So what is the maximum profit you can make? We will copy from the above row because that is the maximum profit we have achieved so far. So we have just copied the 150 from the upper row. In the similar way, if we have knapsack with the capacity of 2, so what is the maximum profit we can make? We can't take the tablet here, so we will just copy the maximum profit from the above row because that is the maximum profit we could able to achieve in the past. So we have copied the 150. Now we have knapsack with the capacity of 3. So can we take the tablet now? Yes, because tablet is also having a weight of 3 lbs. So our knapsack can carry that. So this time, if we take the tablet, we are making a profit of worth rupees $200. And if we are looking into the table, we can see in the past we have earned $150 for the same capacity, right? So what is the maximum benefit you can get? It's $200. So this time we are going to choose the tablet. So we are achieving $200 here. So for the next column, we have a knapsack of capacity 4. For the tablet row, what is the tablet cost? $200. And what is the maximum profit we were able to achieve in the above row? $300. So which one we should choose? $300, right? But here is the twist, guys. To fill this value, now we have two options. Either we can take it $300 laptop or we can take tablet here. So we have to choose very wisely which one we are going to take. If you take the laptop worth rupees $300, you will only get the laptop. But if you choose the tablet worth rupees $200, you will be achieving something which is not visible here. What is that? You will be getting 1 lb of free space because tablet is having a weight of 3 lbs. So you will get 1 lb free space. But in case of laptop, it will occupy the 4 lbs, the complete space. So if you see here, how you can utilize 1 lb of free space. Can you take something more? So 1 lb of free space can be used to take a phone also. So this time we are taking the phone also because we have a 1 lb of free space. So what is the maximum profit you are making here? $200 plus 150, which is 350. So the overall profit you are making is 350 and the laptop is having a cost around $300. So what do you think? The last time we have made a profit of $300 and this time we are able to achieve 350. So what is the maximum profit we can make? 350, right? So you fill the 350 over here. So this is what the maximum profit which we can get. The final grid looks something like this. And here is the answer. The maximum value that will fit into the knapsack is $350, which is made up of tablet and phone. Maybe you think that I have used different formula to calculate the value of that last cell. That's because I skipped some unnecessary complexity when filling the value in the earlier cell. So for us it was very easy to visualize here. But the same thing we have to tell to our program so that it can take a proper decision and come up with an optimal solution which can give you a maximum profit. So how we are going to do that? So now we will try to translate this approach into a code. And before that, we will come up with some kind of formula which can use to fill up this table. Let's assume here items, rows are represented by I and weight columns are represented by a J. Based on that, we can calculate the table value T Ij will be equals to max of ti minus 1j, which is also known as previous max value, or vi plus ti minus 1 j minus wi. Let me tell you what it is exactly, guys. If you want to calculate any cell value inside this table, you can use this formula. First is the previous max value. How you will calculate the previous max value? So whatever the value or cell value you needed, just see the maximum value above that. So you need to use the previous max value. If we are filling, when we were filling this table for the tablet, so the last value, right? So what we can see, fill the previous maximum value which we have achieved, which is a $300. And the second one, we can use the current item value, which is vi plus ti minus 1 j minus wi. Means use the current item value plus value of remaining space. So if you see here, we have used the same thing. We have used the current item value, which is $200 tablet, plus value of the remaining space, which is a 1 lbs. Let's just to highlight here, I have mentioned vi. Vi means current item value, and that value will come from the inputs. So if you see, we have got an input of values, the array, right? Values array. But this array always starts from 0 onwards, right? So that is the reason when you are calculating the value of vi, it means you have to put the value from this value array, and you will use I minus 1 instead of I. Why? Because input array always starts from the 0 to n minus 1. So that is the reason we'll use I minus 1 here. In the similar way, for wi, also we have to use the weight array for that particular item. So if you use the weight array for that particular item, and we know that weight array also starts from the 0 to n minus 1, replace this wi with the weight array I minus 1. So this is a complete formula which you can use to calculate the each cell value. I hope you will be thinking, when I was filling this table, I have not used this formula. But trust me guys, I have used the same formula. Just because whatever we have just filled up, it was very easy. There was only 1 or 2 items. You have not seen the need of it. But this is a complete formula which can help you to fill each and every cell value. So whatever we have done it for the last cell, this 350 is derived from this formula only. So now we got the formula which can be used to solve this, and the same formula can be translated into the code and your code will work. So when you do the step-by-step process guys, you can come up with this formula. Let's see how the experienced people solve this problem. The people who is having a lot of experience, they have a different way of thinking. So they will solve the problem in a different manner. So let's see how they will come up with the algorithm. So every places, it's very clear guys, what are the items you have. Either you will take that item along with you or not, because it's a 0-1 knapsack problem. So either you have to take it or leave it. So based on that, so there will be 2 cases. So either you will choose the item or either not. So suppose in the case 1, you are going to choose the current item. So if the current ith item is selected, so the maximum profit value you can make from this is, if you see the table, this is the values which you can get, and these are the weight, right? So if you are at ith position, the maximum value which you can get is value of the current item plus the maximum profit with remaining capacity, because whatever the element or the item you will choose, based on that, for the next item your capacity of the knapsack will reduce, right? So if you choose the item, and this can be written in terms of formula, something like this. If the ith item is selected, then you will get the maximum value, something value of I minus 1. Why it's I minus 1 guys? We just discussed, because the input array is always start from 0, right? So you use the I minus 1 plus max v is a function which will calculate the maximum value for this problem, and that we have a 2 argument. I minus 1. Why I minus 1? Because the next time if we have chosen such item, that item will not be there. So we are reducing the I minus 1, comma, C minus WT I minus 1. C stands for capacity, the total capacity which we have received, minus WT is a weight array. Why it's I minus 1, guys? That you already know. So max v is basically a function which will solve this problem, and that this is a sub problem. If you are selecting ith item is selected, so in that case the maximum profit which you can achieve is this. Guys, I know maybe it's not clear right now. Just see for some time. What I'm going to tell, just follow the same, then you will understand it in a more better way. In the second case, if you do not choose the current item, so if current ith item is not selected, the maximum profit value you can make is, so this is the array, guys, and if this current item is not selected, the maximum value you will make is the maximum value from the remaining items except the current item, which can be written something like this. If ith item is not selected, the maximum value will be I minus 1. Why I minus 1? Because you have rejected the ith item. So now the item whatever is remaining is I minus 1, and the capacity is still like C, right? So the function will be max of v I minus 1 comma C. Now we will include these two cases in a one single line, and we can derive a relation something like this. There is a function of max v which will calculate the maximum value, which depends on the two things, I and C, where I stands for item and C stands for the capacity. As we have seen, guys, in the last slide, we have to use the table. In table, the ith rows depict the items and the jth row depict the weight. So it only depends on the item and weight. So in the similar way, in our function, the maximum value or max v, it totally depends on the two variable I and C, which can be calculated equals to maths.max, where maths.max of ith item is selected and ith item is not selected. Because at every moment we have two choices with us. It's a 0-1 knapsack, guys, right? So either you will carry that item or you will not. So based on that, you will use this relation, and this relation can also be simplified in a single line something like this. So I have just replaced the value what we have calculated. Now I hope it makes sense, guys, how people derive the algorithm. First, I have showed you the way. If you don't know how to go with the problem, just try to solve the small input and see what the result you are getting. If you are an advanced programmer, you can use this technique directly without using the table filling approach. So now we know the algorithm. Now we'll see our fast method to solve this problem. Guys, those who don't know the fast method, I'll suggest please watch my previous tutorial in a sequence to get the more out of it. So let's see the fast method, guys. So first we are going to find the recursive solution, but before that we should have recurrence solution with us. So this is the recurrence solution which we can achieve from the past. Let's see. We have a function of max v which depends on the two variable I and C. We know I stands for item here and C stands for the capacity, basically a weight. So the first one is if I equals to 0. If there is no item, so what is the maximum value you can get? It's 0. If capacity is less than equals to 0, then what is the maximum value which you can carry along with you is 0, right? If you have a weight, item weight is greater than capacity, so what you are going to do with? You are going to reject that item. So for rejecting the item, you will use max of v I minus 1 comma C. It means you are rejecting that item, so you have removed from the iteration. So instead of I, now you will look for the I minus 1 item. And the next one is if weight of the item is less than equals to C, then you have two choices with you. Either you will take it or you will leave it. So if you will reject that item, so it will be max v of I minus 1 comma C. And if you are taking that item, then you need to get the profit from it, which is a vi plus max of v I minus 1 comma C minus wi. So this is a recurrent solution which you can achieve from the past. Now we'll translate this recurrent solution into our code. So our code will look something like this. We have a function of maxv of I and c. Guys, if you see, I'll just show you how I just translate this code from this formula. If you can see, I have included both the condition if I equals to 0 and c less than equals to 0, the result should be 0. So I am returning 0 over here. Let's come to the next one. If wi greater than c. So here in condition I have mentioned wi means if weight of the item is greater than c. So weight of the item means you have to take the item from the weight array because you have a weight array, and we will use I minus 1 because the weight array item starts from the 0 onwards, right? So we'll use I minus 1. If it's greater than c, then we are going to return max of I minus 1 comma c. And the next is the else condition. So which we have broken down into two parts. If ith item is selected, then we are going to calculate this value from the value array I minus 1 plus max v of I minus 1 comma c minus wt I minus 1. In the similar way, if ith item is not selected, we are going to call this function again with the I minus 1. And at the end, we are going to return the maximum out of it. So I hope guys it is clear to you how I have translated this reconciliation into our recursive algorithm. And by using this method, we can solve this problem easily. The complexity of this algorithm is 2 raised to power n. For those who don't know how 2 raised to power n, I'll just give you a brief introduction here, but I'll suggest you to watch my previous tutorial to understand it. And today I'll show you the alternative way to calculate the complexity. So let's analyze the solution, and that we'll see the complexity also. So this is a problem statement guys which we have got, and this is a reconciliation which we have seen so far. Let's try to use this reconciliation for the given input. As we know, we have 3 items and the capacity is 4. So just put that into this reconciliation. So max of v is 3, 4. 3 stands for number of item, 4 stands for capacity. And we know here we have only 2 options. Either we will choose the item and we will reject the item. So if we are rejecting the item, then this function will make a recursive call with the 2, 4 because that item we are discarding. So we will reduce the I here, which is 3. So now it will be 2, 4. And the second one, if we are going to choose the item, then we'll call the same function with this input, where you will reduce the I and we will reduce the capacity also, because now we have chosen this item, so the knapsack capacity will also reduce. And we know bag is having a capacity of 4 lbs, and if you have chosen the third item, which is having a weight of 3, then only 1 lbs will be remaining. So we are going to call the same function with 2, 1. So in the similar way, if you call this recursively, you will see the tree structure something like this. If you notice this properly guys, you can see in a level 1 we have only 1. In the level 2 we have 2 childs. Basically the one problem is getting divided into 2 parts. In the level 3 it's getting divided into 4. So in the same way, actually it's following a GP. So every time each problem is divided into 2 parts. So it's following the series of 2. 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, something like that. If it goes till the end, it will be 2 raised to power n. So that I will leave it as an exercise for you guys. You can see how the complexity will be 2 raised to power n. But this is just a tree which you will get. Here I have highlighted the overlapping problem. So you can see this problem is calculated twice. Guys, if you draw the complete tree, you will see there are a lot of subproblems which is calculated multiple times. So to save that effort and time, we are going to store that result into a cache so that we can use it later. So in the next step, now we are going to save this result and use it later to reduce the time. Here we are going to save the result, which is also called as memoization. So guys, in that we have 2 variants. First is the cache declaration is on global level. So the global level I have a cache. The cache sizes totally depends on the length of the item, whatever we have, plus 1. and the capacity of the item plus 1. Why we have taken this plus 1, guys? Because we don't wanna use minus 1 for each and every calculation. So that's why we always take array of size 1 extra. As you know, if you are talking about the third row, but in array, it will be a second index because it always starts from the 0 onwards. So to remove that calculation, doing a I minus 1 every time, here we are taking a cache with 1 index ahead. So this is the same program, guys. In that, just we have added a couple of statements. First, we will check into the cache, and if that value is present into the cache, we will return it from there. Else, we will calculate the value and put it into the cache. So this time, we are reducing the recursive call whenever we find some information which has already got processed. We will store into the cache, and then we are returning from there. By using the cache, we are reducing the recursive calls, and the complexity of this algorithm is NC. What is N here, guys? N is the number of items, or you can say the size of the array. NC is the capacity. So this was the first variant, and the second variant will use the cache on a method level. So in this, you can see, guys, we have added one more extra argument into the method, which is a cache. So every time we'll pass cache along with that whenever we are going to call this method. So in that case, we don't need to declare the cache on a global level. You can declare the cache in a local level and call this function, which we will see in our code also. The rest of the things are same, guys. And now we are going to tweak the solution in a bottom-up manner. As we know, the pure DP solution is only the one which uses bottom-up approach. So here, now we are going to use the bottom-up approach. So this is a function, guys, max v, where we have taken a 2 input n and c. Here, why I have taken n? Because I have used I inside this method. Because I represent item, which is more close to the item, so I have taken a I as item. W represent weight, and we have a cache of size n plus 1 and c plus 1. So here we have used 2 for loop. I hope you remember, guys, we have filled this table, right? So this logic will be used to fill this table. If you remember, guys, this is the same table which you have just filled in a couple of time back. So the same thing now you are going to fill in a programming. So there is a 2 loop, one for rows, and we know we have rows for items. So it will go from 0 to n and columns from 1 to 4. So guys, when I showed you this example or table, I started from 1. So there was no 0. But we know when we use in programming, index starts from 0 onwards, right? That's why reason we have taken cache with plus 1. So we will get one extra row and extra column for 0. So in that you can see the condition, if I equals to 0 or w equals to 0, we are going to fill the cache with the 0. So there will be one more layer on top of this right? So there will be one more row of zeros on top of this. And this is the condition which we have already seen. If weight is greater than the knapsack capacity, then we are going to ignore that weight and we'll use the solution which we have calculated above before that. So that's why we are using the cache from I-1 W. Else we are going to use the same formula to calculate the value. And the final is the input. We will return the value from this cache table. So guys, I hope this problem is clear to you, how we have solved the problem. And the complexity of this algorithm is also NC. And we have used the space complexity is also NC. N is the number of rows, the items, max item which we have. The C is the capacity. So this is a pure DP solution, guys, bottom approach. Let me tell you one thing, guys. Whatever we have done initially, the table filling approach, this is nothing, this is the bottom approach. Just because you are starting with the programming, maybe you will not get the recursive solution directly. So sometimes you may be required to break the problem in a smaller subproblem and try to solve it for a couple of values. So if you're trying to do that, that approach is basically called as a bottom approach, because here you are starting from the initial level from 1, 2, 3, something like that. So this is called the bottom approach or the tabulation, which I've already seen initially, but I have not informed you at that moment. So just to highlight, the tabulation or the bottom approach is nothing, it's the same thing, table filling approach. So here I don't need to tell you the same thing exactly how I filled this table, but this table I filled it as a part of table filling, so I don't think we need it here. But this is the same thing which we have done it. So let's do some pattern analysis, guys. Now, so this is a subproblem statement, guys, and you can create a general statement out of it, which is something look like this. And we have already seen this earlier. And there can be any story around it, guys. So don't think that exact same thing you will get in a program or interview. It can be anything, but you have to focus on the general statement, what they are talking about. So this is the general problem statement, guys. And this knapsack problem is the optimization version problem of this problem statement, guys. Let's see the demo part, guys. Guys, please watch this demo carefully, because in that I am going to show you the proof how the table is getting generated and what would be the value inside it. So please bear with me. I know this tutorial is going to be very long, but definitely you are going to learn a lot. And if you have not subscribed yet, please like, comment, share and subscribe, guys. So here is the demo. So this is the method 1, guys. Method 1 approach 1. So in that we have solved this problem using a recursive solution, which is having a time complexity of 2 raised to power n. So this is the method name, guys. Solve knapsack M1 method 1 A1 approach 1. So in that we are accepting two parameters, I and C. I is the number of item and the C is the capacity of the knapsack. So this is the base case where if I equals to 0 and C is less than 0, then we are going to return 0. If there is no item and the knapsack doesn't have any capacity, then we are going to return 0. If the weight of the ith item is more than the knapsack capacity, then this item cannot be included in our optimal solution. If weight is more than the knapsack capacity, so we are going to call this recursive function again by rejecting that item. So we are calling with the I minus 1, right? If ith item is included, then we are going to calculate the value using this formula. And if it's not included or excluded, we are going to reject it. So we are going to use this formula. And at the end, we are going to calculate the max value from these two. So this is the recursive solution, guys. And you can see here we have only passed two parameters, I and C, which is keep on changing for every iteration. So this is the method 1 approach 2, guys. It's the same thing, guys. No other changes apart from this, the input. And that we have used this input because we have declared this input on a global label. But for this method, I just want to show you the different approach, so you can pass the input in a method argument also. Otherwise, all those things are same. Now this is the second method, guys. Approach 1, top-down approach using a cache declaration on a top level. So globally I have declared one cache. You can see here, this is a cache, and rest of the code is same. Here we have just added a check. If the value is present in a cache, we will return it from there. Else we'll calculate it and put it into our cache first. And this is the method 2, approach 2, guys. Top-down approach where cache passed as the method argument. So in that you can see I have passed cache as an argument. Same code, just I have added one more argument as a cache. Now we have a method 3, bottom approach, guys. So in that we have taken a cache, right? And we are filling this. Actually, basically I have name as a cache, but it's a table, guide. So we are filling the table here using the two nested for loop. If I and W are 0, then we are filling the rows with 0. It's the extra rows, guys, because in example whatever I just showed, in that I have not used the extra rows. I considered 1, 2, 3, but actually in programming the index starts from 0, right? That is the reason we have taken extra row and column into the table. And this is the same logic, guys, which we have just seen so far. And I am printing the cache also. I am printing the table, how exactly the value is getting filled. And finally, we are returning this table. So let's run this program, guys, and we'll see the output. So here you can see, guys, the answer is 350. The first approach, recursive solution, is taken this time. The second approach is taken this time. And the DP solution is taken this. DP top down. When cache passes the method argument is taken this time. And this is a pure DP solution taken. Guys, please do not consider this time right now, because in that I am filling the table also. So which will also take some time. So that time also get calculated into that. So I'll say that you can check it, but I'll show you. This is the table which we have filled up. If you remember, this is what we have done: 150, 150, 150, 150, 150, 150, and then 300. And then here it was 200 because you have taken tablet here, and this is the 350. So this is the same thing, guys, which we have filled initially, and after that we told the same thing to our program, which formula it has to use to fill this table. So this is what we have done in that. Program is using the same formula to fill this table. So that is the reason we got the same table. And the answer is 350. I hope, guys, you have enjoyed this tutorial. If you find it useful, please like, comment, share and subscribe. And hit the bell icon for more updates. So guys, just a quick update here. I will not upload the solution immediately on a GitHub. I want you to solve this problem yourself first. So after 2-3 days, you can check out this video again, and that description I will mention the link for the source code. Thanks for watching, guys.